Hi, this is Nick Pizzi, and this is another example of softening in our series for water treatment plant operators. I'm going to share this screen with you so that you can catch up with us today. It's a special day because we have a guest lecturer for us today. I'll share that with you in a little bit. But this is the third in the series of practical math for lime softening and water treatment plants. This is aimed at operators who are working in lime softening plants, lime soda process, and who are training for their license exam. This module is a follow-up to the first and second modules that we did. So let me share this screen and go from here. Now you remember in the first two videos of this series on lime softening, we discussed the basics of lime softening. We did the traditional precipitative process. We tried to keep it a little bit simple. We talked about why we consider some source waters hard, why that might be objectionable to some of our consumers, and why we want to soften in the first place. Then we went on to discuss the chemicals that we have to add to the water to remove the hardness, and which chemicals do contribute hardness to the water and to what degree. We reviewed the treatment processes that we employed in the lime softening plants. And then we did some of the math problems that are typically associated with the license exams that we take. We provided a line diagram of a water treatment plant. We provided some actual problems and worked on those. We showed the chemical formulas for the hardness compounds of water and how the addition of lime and soda ash work to remove some of these. And the following slides, of course, are some of these traditional formulas. I want to go over them one more time, even though we covered them at length in the first two videos. This is the chemistry of the lime soda process. I mentioned that these equations, we're adding either lime, which is calcium hydroxide, or soda ash, which is sodium carbonate. I think we mentioned back then that we could use caustic soda, but we're not covering that in any of these videos, but a lot of plants do use that too. So we have 9 traditional formulas that you see here, and what's common to all of them is that they either have a calcium compound or a magnesium compound contributing hardness to the water. And of course, we want to add lime or soda ash to remove those. Some things I can point out to you, of course, are that the equations show how the precipitative treatment converts soluble calcium and magnesium compounds to the insoluble calcium carbonate and magnesium hydroxide. I even told you that after those two compounds, we often put a down arrow to show you that these indeed are precipitates. Note that in equation 2, magnesium carbonate is formed, so we have to add more lime. So we got to actually get twice the lime to take out the magnesium carbonate compounds that we have. So this becomes a complex issue, and we have to really work hard to get our dosage formulas. Today, hopefully, we're going to find a different, an alternative way to calculate our dosages, and we're going to have an expert that's going to show us how to do that. The last thing I do want to mention is that if you look at equations 4, 5, and 6, we do form magnesium hydroxide as planned, but we also form 3 insoluble calcium compounds, which are non-carbonate hardness. We have to then add the soda ash to remove them, so we want to keep that in mind. And it's helpful if you could print this page out while you're at it, if you could do a screenshot and print it out, or if you're watching the video for the first time and you want to stop the video here and do a screenshot and print it out. It's helpful to be able to refer to that as we go through the equations that we're going to cover in some subsequent slides. When I did the first 2 videos, I mentioned that a lot of that material came from a book called Hoover's Water Quality and Treatment Book, and that was the 12th edition, which was done back in 1995. I did a little bit of work on that, but in chapter 10 in the book, I had to go out, because this part was pretty much over my head, I had to go out and get a friend of mine who could explain some of this to us, and we have him, luckily, with us today. We're going to talk about the milliequivalent per liter process to explain the lime and soda ash requirements that we need. So that section, which was done way back then, was done by Dr. Tim Wolf, who's with us today as our guest lecturer. So let's welcome Tim Wolf. There's Timmy boy. Dr. Wolf, of course, has delivered hundreds of PowerPoint presentations to our operators all over the U.S. He currently is the Vice President Emeritus of Stantec Consulting. And lately he's been working at The Ohio State University with the EE Capstone course and doing some great work for Ohio operators in that. He did author that work, as I mentioned, in the lime softening chapter in the lime book. And with that, I'm going to turn it over to Tim, and he can pick it up from here. Tim, thank you.
Thanks, Nick. It's always a pleasure to work with you. So let's talk a little bit about milligram per milliequivalent conversions, and then a little bit about why we even use milliequivalent per liter. And it makes you'll find out it makes things a lot simpler. but let's talk about why. So milliequivalents of any element, ion or compound, can be determined by using the formula where you divide by the milligrams per liter of element or compound, multiply by the valence, divide by the atomic weight. And you see the example there where 80 milligrams of calcium ions becomes 4 milliequivalents of calcium per liter. And it's real simple. It's just knowing that it takes into account the valence, and makes this, as you'll see as we go forward, makes this a lot simpler to do because of a certain reason I'm going to tell you. There are various tables, nomographs that can make the calculations easy, but we're going to use a simple bookkeeping method that I think makes softening a lot simpler to understand. It's not a mystery. There are all sorts of these example tables, videos, nomographs to be found. But advantages of using milliequivalent per liter are that one equivalent of anything produces one equivalent of anything. So when we convert to milliequivalent per liters, it makes it very simple that if we've got calcium bicarbonate, like in equation 1, milliequivalent per liter wise, we create 1 calcium carbonate. Now, as you see, I don't need equation 1 in front of me. It's nice to have it. I encourage you to use it. But now, if I don't have that equation in front of me and I use milligrams per liter, I need to know that there's 2 moles of calcium carbonate created on the right-hand side. I need a balanced chemical reaction. So it's a lot simpler to use milliequivalents per liter because 1 milliequivalent of anything creates 1 milliequivalent of anything. And just let me preface that, because sometimes might take me too much verbatim. That doesn't work so well when we're talking about a different kind of chemistry, which is oxidation reduction. For instance, if I'm trying to precipitate iron that's a ferrous as a ferric, well, in that case, there's a valence change. So 1 milliequivalent doesn't create 1 milliequivalent, where it does here, because calcium remains +2 on both sides of the equation. Magnesium remains +2 on both sides of the equation. There's no oxidation reduction going on here. This is, in chemistry, sometimes we call this the common ion effect. I'm trying to precipitate calcium carbonate. So the more carbonate I have around, they join up and they precipitate. The more magnesium hydroxide I have around, I precipitate magnesium. So there's no oxidation reduction going on here. So milliequivalent per liters really work well because 1 equivalent creates 1 equivalent. So let's talk about how to develop this milliequivalent bar graph. Next slide. So we're going to do some example softening strategies. We'll show you an example that provides an illustrative approach, and it's a single stage so that it's simpler to understand. And then we'll talk a little bit about how you can apply those same techniques to 2-stage softening with excess lime or split treatment softening or whatever type of softening you might be doing at your particular water treatment plant. So in this example we're doing, again, it's single stage softening, and magnesium is not excessive, so we don't need to go to 2-stage to raise the pH, and we'll talk about that a little bit later. This has a source water that also contains dissolved carbon dioxide, often does, and we'll show you how we insert that into our graph so that we keep track of it, because we don't really want to remove the carbon dioxide, but we don't have any choice. The lime is not that smart. We put it in there. We tell it to go precipitate calcium and magnesium, and it finds carbon dioxide and precipitates it. So we have to take account of it, but we'll keep it separate in our diagrams so we don't get confused, because carbon dioxide is not hardness. We will then we'll show some source water analysis for this example and the chemical requirements and softening water characteristics. So here's the example source water analysis. And please always note that we will develop our graphs based on positive ions on the left-hand side and negative ions on the right-hand side. And we will also developing our graph so we can do this simple, what I like to think is simple bookkeeping method by listing them in this order. So calcium first, magnesium second, sodium, potassium, any other cations that we want to include because they're of significant concentration. I want to do this because, first of all, calcium and magnesium are in fact hardness. Sodium and potassium are monovalent. They are not hardness. Hardness is divalent cations. And almost always it's pretty much calcium and magnesium. Likewise, on the right-hand side, we want to list the negative ions in this order also. We want our alkalinity, bicarbonate in this case, and we report it usually as calcium carbonate, whether it's a combination of carbonate and bicarbonate, but we want to list our alkalinity first, and then we list the sulfate and chlorides. And so what we're really doing here is we're not only listing cations on the left, anions on the right, but what we're doing is saying, look, guys, the hardness compounds we're going to list first on the left, and on the right, we're going to list the alkalinity followed by sulfate and chloride because those are our non-carbonate hardnesses. And if you go back and look at your equations again, you'll remember that 1, 2, and 3 dealt with carbonate hardness. 4, 5, and 6 dealt with carbonate hardness, but with additional lime added for the magnesium. And then 7, 8, and 9 actually talk about non-carbonate hardness. So we want to list our carbonate, our alkalinity first on the right. And then the source water, again, has 22 milligrams per liter of dissolved CO2, but again, we'll keep that separate because we really don't want to precipitate that. It's not hardness, but we have to. So the conversion. Now that we know the ionic makeup of our source water, it's time to convert milligrams per liter to milliequivalent per liter representations. So that way, we again can use a graph or a table, however you want to call it, that says 1 milliequivalent of anything creates 1 milliequivalent of anything. So we can use these traditional formulas. We don't need a balanced chemical reaction. We don't need to know how many moles of what create how many moles of anything on the right-hand side because we're talking anything as a milliequivalent on the left-hand side of the equation produces 1 milliequivalent on the right-hand side of the equation. Makes life a little simpler. Next slide. Next slide, please. So I like to do my bar graphs. Oh, our softening example is single stage softening using lime and soda ash. So we're going to do complete softening and we're going to take out both the carbonate and non-carbonate hardness. So as you see here, I'm listing, we've converted these concentrations in milligrams per liter to milliequivalents per liter. And the calcium, we have 6. Magnesium, we have 2 milliequivalents per liter. Sodium, for the source water, we have 1. Potassium, we have 1. You notice I listed carbon dioxide above 0 because, again, I'm trying to do a lot of stuff when I have a graph like this. First thing I'm doing is I'm saying, oh, what's my total hardness? Well, 6 plus 2 is 8 because it's calcium and magnesium. So that's why I list carbon dioxide up on top. Also, I list CO2 on top because, again, it's not hardness, but I have to remove it. On the right-hand side, we've listed our anions. Bicarbonate hardness turns out is 5.5 milliequivalents. We have sulfate is 2.5. Chloride is 2 milliequivalents. So now you can see, we can look at this graph and say, okay, now let's do, we know the compounds that are theoretically or hypothetically there, and we can go across using the equations. Again, equations 1 through 3, 4 through 6, and 7 through 9 are available to you and explain everything we're going to put on this graph. So first thing I got is CO2. Don't want to remove it, have to remove it. This is a pH game we're playing. Got to get the pH up. I've got to neutralize the sodium or the carbon dioxide. So for 1 milliequivalent of CO2, I need to add 1 milliequivalent of lime, and that will produce 1 milliequivalent of calcium carbonate. Okay, so 1 lime. Now I've got 6 calcium, but only 5.5 alkalinity. So you see I drew a dotted line there across at 5.5 because I've got 5.5 milliequivalents of calcium bicarbonate. And you go back to the first of the 3 equations. You know, I can't remember, but it's 1, 2, or 3. I think it's number 1, but it's 5.5. Again, we're dealing in milliequivalents per liter. So 5.5 calcium bicarbonate require 5.5 milliequivalents per liter of lime. It produces nothing but calcium carbonate, so there's no need for soda ash, so that's a big 0. Moving down, and again, this is why we always list these compounds on the left and on the right in the order we list them. We now have half of milliequivalent per liter of calcium, or calcium sulfate. Calcium sulfate. You see that? That's a 0.5 milligram per liter, or milliequivalent per liter of calcium sulfate. Well, that's non-carbonate hardness. So we don't need any lime, but we need a 0.5 milliequivalent per liter of soda ash to convert it to calcium carbonate. Okay? Now we go down a little farther. We've got a dotted line across at 6 that says to me that, well, we've got 2 milliequivalent per liters of magnesium sulfate, right? And that requires 2 milliequivalent per liters of lime. That will produce magnesium calcium carbonate, but I'm sorry, magnesium hydroxide, but it also gives us a calcium sulfate. And you go back to the equations, you'll see that. And so I need 2 more milliequivalent per liter of soda ash to take care of that calcium sulfate and take it over to calcium carbonate. Because remember, everything on the right-hand side of the equation at the end of the day, if we want to precipitate calcium, it's got to be calcium carbonate. And if we want to precipitate magnesium, it has to be magnesium hydroxide. That's the only way this works. Okay, we go on down. Sodium, we got sodium chloride. We've got 1 milliequivalent per liter, not hardness, don't care. We got 1 milliequivalent per liter of potassium chloride, don't care, not hardness. Add up all my lime milliequivalent per liters. I've got 8.5 milliequivalent per liter of lime and 2.5 milliequivalent per liter of soda ash to fully soften this water. Okay, and I'll explain in the next slide and beyond what we mean by fully softening. So this is a single stage softening using lime and soda ash. And the single stage example is, and a lot of plants are like this, you've got 1 rapid mix, 1 flock tank maybe, and a settling basin. And that's what we show settling there, mixing and settling. And then you recarbonate after you've added the lime and soda ash to the first stage. You recarbonate, bring the pH back down, and any calcium and magnesium remaining, escaping the settling basin, you convert back to its soluble form so we don't make our filters the world's largest marble test. The sand media is not there, nor is the dual media there to precipitate your hardness on. So we need to recarbonate. And since the softening reactions take place in 1 reactor, and we add the stoichiometric amount, that gives us a pH of 10.4. And that is ideal for precipitating calcium. Okay, and we'll talk about that on the next slide. It's okay for precipitating magnesium hydroxide, but the ideal pH for precipitating magnesium hydroxide is a pH of 11.2. So we can't operate that 1 settling basin at 2 different pH values. So that's why we choose to do in single stage softening stoichiometric amount of lime, stoichiometric amount of soda ash if we want to fully soften the water, and we end up with operating the basin at a pH of about 10.4. Okay, so at 10.4, escaping that first basin, we are going to have 30 milligrams per liter of calcium carbonate escaping, and we're going to have 30 milligrams per liter of magnesium hydroxide escaping as calcium carbonate. So let's talk about this example. Let me repeat the first one, the first part of it, so that we make sure we drive this home. So there's our milliequivalent per liter bar diagram, same one we looked at before. And here's how we came up with those milliequivalent per liters. Calcium, we said in our source water back several slides ago, was 120 milligrams per liter as calcium. We divide by the equivalent weight of calcium, 20 milligrams per milliequivalent. Cancel the units, milligrams cancel milligrams. We end up with 6 milliequivalents of calcium per liter. We go down to the magnesium, same thing. It's 24.4 milligrams per liter. Divide by the equivalent weight of magnesium, and we end up with 2 milliequivalents of magnesium per liter. Sodium the same way, potassium the same way. Right-hand side, a little bit different, not much. I'm sure you've seen this over and over. We like to talk about alkalinity and hardness and those kinds of things in terms of their equivalent as calcium carbonate. So we're reporting the alkalinity as 275 milligrams per liter as calcium carbonate. So we divide by the equivalent weight of calcium carbonate, 50 milligrams of calcium carbonate per milliequivalent, and cancel the milligram, and we end up with 5.5 milliequivalents per liter of alkalinity. In this case, it's all bicarbonate. Could be hydroxide, could be carbonate, could be bicarbonate. But in majority of the cases, it's going to be predominantly bicarbonate because of the natural pH of the waters that we tend to get out of groundwater sources. Sulfate, same way. We divide by its equivalent weight. Chloride and CO2 again, we list at the top because again, we have to neutralize it to get the pH up to 10.4. So we're going to have to add lime to remove it, or as calcium carbonate, basically. So again, we go down again. I draw my dotted lines at 5.5 and at 6 and at 9 so that I can go straight across and talk about what kind of lime I needed for each amount. And you can see here, again, we have 1 milliequivalent per liter because there's no oxidation reduction going on here. It's just common ion effect. And I precipitate CO2 as calcium carbonate with 1 line because I have 1 there. Got 5.5 calcium bicarbonate. I add 5.5 milliequivalents per liter of lime, and it all precipitates as calcium carbonate. I got 0.5, 6 minus 5.5 there of calcium sulfate, 0.5, and that is non-carbonate hardness, and it's calcium, so I simply add soda ash to convert it to calcium carbonate. I got 8 minus 6, or 2 milliequivalents per liter of magnesium sulfate. That is non-carbonate hardness, but it's non-carbonate hardness with magnesium. When I add the lime, I precipitate magnesium, go to magnesium hydroxide, but the problem is I've got calcium carbonate that is formed, and I have, or calcium sulfate, and I have to add 2 milliequivalents of soda ash, just like I did in the line above, to convert it to calcium carbonate. Again, sodium chloride, potassium chloride, not divalent, they're monovalent, +1 ions, don't contribute to hardness, don't have to soften them. So as we did before, we came up with 8.5 milliequivalents per liter of lime and 2.5 milliequivalents of soda ash to add to the first stage, only stage. The pH will be at 10.4. And now let's see what happens when we do that. Next slide, please. Let's go to the next slide. So CO2 must be dealt with. Again, we don't have much choice. And if I add lime to CO2, I produce calcium carbonate. Go back 1 slide. Go back 1 slide, please.
think that's the slide you want there.
No, I was going to do the other one.
This one?
That one. Yeah.
Okay.
And again, you can see the 5.5 milliequivalents of calcium bicarbonate produces calcium carbonate. I'm done. The 0.5 milliequivalents of soda ash reacts with the calcium. I need that slide. It doesn't want to stay up, or?
That slide or this slide?
No, the other one. Next one. We don't want to use that slide. That slide right there. I'm going down it.
Which heading are you looking for? This is example one, step one, continue.
Yeah. That's fine, but I'm trying to read it.
Oh,
and you keep taking it away.
There's got to be a challenge, Tim.
So we have 5.5 milliequivalents, as I said, of calcium bicarbonate. It produces calcium carbonate. Again, if you go back and look at your chemical reactions, a 0.5 milliequivalent per liter of soda ash is needed for calcium sulfate, and it converts it to calcium carbonate. Everything's fine. 2 milliequivalents of lime reacts with magnesium sulfate, and as I said before, it produces magnesium hydroxide, but it also produces calcium sulfate. So now I have to soften that non-carbonate hardness with 2 milliequivalents of soda ash. And the lime and soda ash are not required to react with the monovalent potassium and sodium. Next slide. So here's kind of what we're doing. We're going to add 8.5 milliequivalents per liter, and that's lime, and 2.5 milliequivalents of soda ash. So if you're using quicklime, CaO, you've got 8.5 milliequivalents per liter. You multiply it by its equivalent weight, 28 milligrams per milliequivalent. The milliequivalents cancel out, and you end up with 238 milligrams of calcium oxide, quicklime, to soften this water fully. 8.5 milliequivalents per liter. If I'm using hydrated lime, I multiply by its equivalent weight, 37 milligrams per milliequivalent, and therefore I end up with 315 milligrams per liter of calcium hydroxide hydrated lime to soften this water stoichiometric amount. Soda ash, 2.5 multiplied by its equivalent weight of 53. I need 133 milligrams of soda ash, sodium carbonate, to soften the non-carbonate hardness. Next slide. Next slide, please. There we go. So, leaving first stage settling is, I said earlier, 0.6. I said 30 milligrams per liter of calcium carbonate as calcium carbonate, and 30 milligrams per liter of magnesium hydroxide as calcium carbonate will leave the first stage because the pH is 10.4. I have to raise the pH up higher if I want to get the magnesium level lower. Okay, so 30 milligrams per liter, you can see on the right-hand side over there, divided by the equivalent weight of calcium carbonate is 0.6 milliequivalents per liter. So we have calcium carbonate, 0.6, magnesium hydroxide, 0.6, sodium, 1. We didn't do anything to the sodium, but we increased it by 2.5 because we added soda ash. Okay, so now and potassium is still 1. The sulfate is still 2.5, and the chloride is still 2. Okay, the beautiful thing about doing this vertically is that, number one, it's a nice, easy bookkeeping method. And the other nice thing about it is, unless your analytical work was not correct, cations will equal anions. So we will always end up with the same total on the left and on the right. Last time it was a little higher because we hadn't softened the water yet, but now it's 5.7. But there's still 5.7 on the left, cations, 5.7 on the right, anions. So that's a nice check. Now we need to add CO2 before we hit the filters. We don't want the stuff to precipitate on the filters. And so if I add 1 CO2 to calcium carbonate, I produce calcium bicarbonate. Life is good. If I add 0.6 or 1 milliequivalent, per milliequivalent of magnesium hydroxide, I take it to magnesium carbonate. That's not far enough. So I need to add another 0.6 milliequivalent per liter of CO2 to take the magnesium hydroxide from magnesium hydroxide to magnesium carbate to magnesium bicarbonate. So I need 2 milliequivalents for every 1 milliequivalent of magnesium hydroxide. The first CO2 takes it to bicarbonate or carbonate, second one to bicarbonate. Okay, next slide, please. So now we can go to our filters without precipitating all over them. And we've got 0.6 milliequivalents, as I said, of CO2 reacts with the calcium carbonate. We got the equation 2 there. You see we can create magnesium carbonate, so we have to go to equation 3 and add another CO2 to create magnesium bicarbonate, so we don't precipitate magnesium on our filters. And the approximate carbon dioxide that must be used to recarbonate is therefore 0.6 plus 0.6 plus 0.6, or 1.8, and times its equivalent weight, we end up needing about 40 milligrams of CO2 per liter to recarbonate this single stage example. Next slide, please.
Tim, if I could interrupt you, I appreciate you saying that, because I know a lot of operators have difficulty making that decision as to how far they should recarbonate before they put water through their filters. And you and I both know that a lot of them use their filters to recarb, so to speak. So it's especially good that you explained it the way you just did. Thank you.
You're welcome. And I think it's also important, Nick, because we have to keep in mind, a lot of softening plants will use sand media only. Some will use dual media. And we defeat the purpose if we precipitate on anthracite and make it heavier, and so it doesn't stay on top of the sand. So I've seen a lot of dual media filters in softening plants where not recarbonating sufficiently, they end up with a mixture of anthracite and sand, not anthracite on top of sand. So the filter doesn't operate the way it was designed to operate necessarily. So the water applied to the filters, like I said, you want to have hopefully calcium and magnesium bicarbonate, so we don't precipitate on the filter media, change its specific gravity, or worse yet, I've seen single stage softening plants that have sand only, and if you did an analysis of the equivalent, the effective size of the media after about 10 years, it went from 0.5 to about 5. I won't talk about the water plant in Iowa. When I was in grad school many years ago, the operator, we were showing the students this particular water plant, and he was very proud of the fact that he had never had to add filter media. He just scraped off about 2 inches every year and threw it away. But he had marbles in the filter, not sand. So we got to be careful. We got to be careful. Okay, next slide, please. Next slide, please. There we go. So there are other examples in the line book, softening of water, and you're encouraged to read those and go through them. I want to talk a little bit about them, though. We don't have enough time here today to go through them, but I want to talk to you about why we would use those other types of softening methods. They're still precipitative softening, but different ways of operating a two-stage system instead of a single-stage system. Okay. So let's talk about those a little bit. Next slide, please. So the other examples follow the same bookkeeping method that I think is very simple. Again, we made it overly simple, I think, because I love the fact that 1 milliequivalent, as long as there's not an oxidation reduction reaction going on, 1 equivalent of something reacts with 1 milliequivalent of something and it produces 1 milliequivalent of something. So it makes life pretty simple. So we're going to talk about a 2-stage excess lime softening, and we're going to talk briefly about what I call split treatment softening, which a lot of people suggest they might be doing, but it's rarely used. But it's a wonderful process, particularly in today's world of making sure you have simultaneous compliance with the finished water that also has to take into account lead and copper rule and that kind of stuff. So let's talk a little bit about those things in 2 stages if you have that in your plant with 2 sets of clarifiers in series. Next slide, please. So I like this. It kind of summarizes the whole big picture of what you can do with, and notice the word full. Please keep that in mind. Comparison of full, single, 2-stage, and split treatment softening. A lot of you and most of you probably aren't going to do full softening, and we'll talk about that. And so you just simply don't add all this lime and soda ash, and you go through the same bookkeeping method. But let's talk about it. So in single stages, we went through an example. We said, where are we going to operate it? Well, we're going to add the stoichiometric amount of lime, stoichiometric amount of soda ash, and the pH is going to be 10.4. And in the first stage, recarb, we're going to take the carbonate to bicarbonate in the case of calcium carbonate. In the case of magnesium hydroxide, we're going to convert it first to magnesium carbonate with 1 CO2 and then to magnesium bicarbonate with another CO2. In the second stage, there is none, so it's not applicable. And the second stage recarb, likewise, not applicable. But if I operate a 1-stage full softening, stoichiometric addition of amount of lime and soda ash to soften everything I can, full softening, I end up with 30 calcium, 30 magnesium as calcium carbonate, or a final hardness of 60. Okay, that's about as soft as you ever want to get your water. And most of you don't want to get it there. In fact, I would guess that most of you have a goal of softening somewhere between 100 and 150 milligrams per liter finished water hardness as calcium carbonate. So as you can see, I don't really need to do full softening. I don't need to add the stoichiometric amount of lime and soda ash typically, but I can simply calculate my finished water by doing the same example, putting my milliequivalent per liter bar diagram in vertical and calculating how much lime I do want to add. And so I don't add it all, or I don't add all the soda ash. And it becomes very apparent what my final hardness will be. Now, 2-stage is kind of nice in that I can add excess lime. And I call it excess lime because I add typically about 1.25 milliequivalent per liter of excess lime. And what I do is I'm using that excess lime to raise the pH to 11.2. And that's great for precipitating magnesium as magnesium hydroxide. So again, first stage recarb, CO2 takes the carbonate, calcium carbonate to bicarbonate, and it takes the magnesium hydroxide to carbonate, and it takes the excess lime to carbonate. It's 2-stage, so I don't add 2 CO2s for every magnesium carbonate. I only add 1. But now I have to, look at what I have to do. I have to add CO2 to my excess lime to precipitate it as calcium carbonate in the second stage. So in today's world of worrying about residuals, when I add excess lime, I got to precipitate it. And keep in mind, when I'm adding lime to precipitate calcium, I'm producing twice as much residuals. So these are the other things we have to keep in mind. So my second stage, now that I've added partial recarbonation, I'm down to 10.4. I'm ideal for carbonate, calcium carbonate precipitation. So my finished water now is 30 calcium and 10 magnesium. Because I operated that first stage at 11.2, I can get my magnesium down to 10. But again, that's 40 milligrams per liter of calcium carbonate. And that's pretty soft, pretty soft. So nice. So why do we even have two states? We want to spend money on concrete, have two bases, or what? Well, here's the reason. Because you can do split treatment. And a lot of you are doing things you call split treatment. What you're doing is maybe routing about, in a two-stage water plant, you're routing maybe 15%, 10 to 20% of water around the first stage, so that you can use that source water CO2 to recarbonate after the first stage. But that's not split treatment. That's recarbonating with source water CO2 levels in the first stage recarb. That's what that is. Split treatment, you're not going to bypass the first stage with 10 or 15%. You're going to probably be close to 50% of the water. And what you do is, if you look off to the right, let's cheat a little bit. The last square on the right there says, I do a magnesium mass balance, and I determine the magnesium level that I want in my finished water. That determines whether that is 25, 30, 35, 40, 45, 50% bypassing the first stage. And this becomes important because in the world of simultaneous compliance, we not only have to worry about how much our finished water alkalinity is, what our finished water buffering capacity is. In many cases, we're concerned about Larson's ratio. We're concerned about calcium to magnesium ratios. All come into play in making sure that we have water that is stable and suitable for meeting the lead and copper rule. So this allows me to adjust my calcium to magnesium ratios. And also, as you see in the second column, pH equals 11.2, but I haven't added any excess lime. Because what I'm doing is I'm only softening 75 or 50 to 75% of the water. So I get a pH of 11.2 by adding the stoichiometric amount of lime, but I'm not really adding excess lime. So I don't have to recarbonate it in the first stage. I also don't have to add CO2 in the first stage because I've got the source water CO2 that can do partial recarbonation and take the pH down to 10.4 for the second stage. Then I recarbonate the second stage to get my carbonates over to bicarbonate so I don't precipitate on my filters. And the magnesium level in the far right is determined again by a mass balance that determines how much water I want to route around first stage. Okay, so it's a very helpful method of softening if I've got two stages to use split treatment. But let me remind you that most of you, if you look at the final hardness values in that finished water on the far right column there, most of you are not going to add the stoichiometric amount of lime and soda ash. You're not going to soften the water down that low. Okay. Next slide, please. So this is our two-stage. Like I said, the excess lime. The problem with the excess lime is I have to precipitate it in the second stage. So I have to add CO2, cost me more CO2, and I produce more sludge, more residuals, we call it these days. With split treatment, I don't have to do that. Okay. I can do, I can save money with split treatment if I do two-stage, and I can also control my calcium and magnesium level. And sometimes that becomes important. There have been reported cases of people scratching their heads because they're flunking lead and copper, particularly lead, but their water seems fine. They got, they got 50 milligrams per liter of alkalinity as calcium carbonate at least. They've checked their buffering capacity is good. So, but they still have problems with lead, and sometimes it's Larson's ratio that we don't always look at, or it's calcium to magnesium ratio. And with split treatment, I can actually control the calcium magnesium ratio. Okay. So that's kind of the other examples. They're a little more complicated, more steps, but follow the same procedure we did for the stoichiometric full softening single stage example. And again, it's real simple. If you don't want to soften fully, you just don't add as much lime or as much soda ash. and whatever you've not added, what's on the left shows up on the right of that bar graph. So life is pretty simple. Next slide, please.
Okay, I guess that's about anything else you want to sum up, Timmy?
No, go ahead. Final thoughts there, Nick, please.
Okay, well, I want to say thank you to Tim. Dr. Wolf, of course, is very well known here in Ohio. If you operate a water treatment plant here in Ohio, you've been fortunate enough over the years to learn many, many things about water treatment from Dr. Wolf. Across the country, he's well known also because of his association with some very good engineering firms over the years. So we're very fortunate to get some of Tim's time today to help us with this video. So this was part 3 of the video series that we're putting together for softening. The first 2 were traditional methods of softening. And today's topic was the equivalent, milliequivalent per liter softening examples that Tim so adroitly explained to us. So check back after you've had a time to digest this. We'll have some other videos that we'll do down in the future if we can talk Tim into giving us some more of his valuable time. And you can access more of those videos by clicking on some of the links that will appear when we put the video together. They'll start to scroll up and you'll be able to take it over from there. So again, Tim, thank you very much. We appreciate your examples for us today and the time that you've given us. And with that, we'll say goodbye.
Thanks, Nick. Good working with you.
Great.